Okay. Hello, everyone. Thank you for joining the session today. We have Dr. Erica Fischer, an assistant professor at Oregon State University, and she'll be talking about OpenSees and fire challenges and future work needed. So this is the first time we are having a session about fire, so it's interesting. Thank you, Erica, for being here. It's all yours now. Thank you.
Yeah, thank you so much. Thank you for inviting me. I'm very excited to be here. I do want to warn you all, I'm kind of a new OpenSees user, so please be kind with your questions. All right. So I mean, there's only a few of us, so feel free to just, I'll keep the bar open on my screen. So if you have questions, feel free to unmute yourself and ask, or put it in the chat, and I'll try to answer as we go along and keep it informal. So I am at Oregon State University, and my background is in steel structures and fire, although now I work on timber structures as well. But I thought today I would first just catch everyone up. So give you a bit of a background as to what are the important things to focus on when you're modeling and simulating steel structures in fire. And what have we been doing here at Oregon State University, and how can all of you also partake in this great research topic and help further along the field. Okay, so the first big chunk of the presentation is really just talking about steel structures and fire in the general sense. Okay, so fire poses a pretty unique threat to our buildings, and it can be in one of two events. So first, you can just have just a fire in a building. So you have an undamaged structure that is resisting the effects of the fire, and then but you can also have fire as a cascading effect. So it can be post-earthquake fire. We're seeing a lot of that throughout the world, where we have some sort of damaged or deformed structure, and then we have a fire. So the simulation software is used to simulate both of these types of events, and these are both types of research that are very important in today's environment. Okay, so we've seen buildings collapsing due to fires, due to cascading fires, and then just due to regular fires. And some of this is, One Meridian Plaza is from Philadelphia in the United States. World Trade Center collapses. One of the more notable fires in a building. The building on top is one of the towers, and then the destroyed and collapsed structure that I'm showing below is actually World Trade Center 7. This is one of the first documented instances of a steel structure actually fully collapsing due to pure fire. And then more recently, we had the Plasco building in Iran that collapsed due to a fire. And so this is happening throughout the world, and our structures are not behaving as we think they are in a fire. And there's a lot that we can do to simulate our structures in fire and create more robust solutions. So there's two methods of approaching this, and so I think it's important for me to address this. There's first is the prescriptive fire protection design. This is really the traditional approach of fire protection design, particularly here in the United States. If for anyone who's in Europe, what's shown on the right might seem a little bit more familiar, but in the United States, at least, this prescriptive fire protection design is very common. This is in the International Building Code, and it's in the form of this hourly fire resistance rating. Without any calculations at all, you're determining how many hours of fire resistance rating that you need on an individual structural member, and then that hourly fire resistance rating corresponds to some sort of thickness of fire protection. So there's absolutely no calculations. You're not using any of the concepts that you learned as in your civil engineering degrees, so you're not using structural mechanics. You also aren't really considering fires that are specific to the building itself. So you're not considering the contents of the building, and you're not considering the shape of the building or the size of the compartments. So structural fire engineering, though, is the design, actually using our structural engineering knowledge to design our buildings for fire. So you're working with fire dynamic specialists. Sometimes they're one and the same. So please note that I am in the United States, and those two fields are very decoupled in the United States. So here we work with our mechanical engineering colleagues, people who are experts in fire dynamics, to calculate what the fire is within the space itself. And then we, as structural engineers, can look at what the structural response is to that fire. So we can actually design our building to maintain load carrying capacity throughout a complete burnout fire. And I'll talk a little bit more about what all those words mean. But really, our goal is to design a building for fire as we would design it for an earthquake. So actually looking at what the forces are in the members and designing them. So this is really where the research lies. Okay, so we're considering building specific fires, structural analysis of building, we're considering temperature dependent material properties, we're looking at load redistribution, and so the research really doesn't lie in this prescriptive fire protection design. Actually, not at all. So when I talk for the rest of this presentation, I'm going to be focusing on structural fire engineering. This is also interchangeable with performance-based fire design. Some people are calling it that. Right now, we don't approach this in a probabilistic way. So I'm calling it structural fire engineering. It's a deterministic method. Okay, so like I said, we're designing our structural components for the loads imposed during a fire event. All right, so what does that mean? So what this means is that we have a fire, our structural components are going to heat up, and then simultaneously two things are going to happen. We are going to have thermally induced forces and deformations. So we're going to have forces and deformations that are not considered at ambient temperature. And we're going to have degrading material properties. Our strength and stiffness of our material is going to degrade as we have these additional forces and deformations. Okay, so you can see already what the problem is here, right? This is why our buildings are collapsing. We have some additional forces in our members that we didn't consider during the initial design of the building. And at the same time, our strength and stiffness of our structural members is decreasing. Okay, so the role of the fire protection is really in this first box, is this second box up here, this heating of structural elements. If we prevent our structural elements from heating up, from reaching some certain temperatures, then we can reduce our thermally induced deformations forces. We can also reduce the degradation of the material properties, or without a double negative, we can prevent the degradation of the material properties. So it's one method, so putting more fire protection on some of our members. The other method is we can actually design our members to withstand this. So our members will be oversized, so they'll have extra capacity in order to resist our thermally induced deformations and forces as we are degrading the material properties. The field of structural fire engineering covers both of those instances. It's really up to the designer as to which kind of road they're taking. But the fact that we have the knowledge and the ability to analyze our structures during a fire allows us to kind of take those paths. Okay, so all throughout this, our gravity loading is remaining constant. So it is almost kind of the opposite of seismic design. So our forces are not, our imposed forces are not changing during the fire. Rather, our material properties are degrading. So we do have these extra forces here. So it's not totally the opposite, but it's one way to think of it for all the earthquake engineers out there. So, we don't actually consider, one thing I do want to address is load combinations, and I do realize this is the, this is from US codes. But it is even in your code, there is a different load combination for an extreme event. So this is taken straight from the American Institute of Steel Construction specification, where this is taken from also ASC 7. And so we have a reduced live load during the fire, okay, because it's considered an extreme event. But there is in this load combination this A sub T factor. So that is these additional forces and deformations due to the fire. So you see it even in a load combination for this extreme event, the nominal forces and deformations due to the design basis fire. And just for those who are not in the US and want to take a look at this, the AISC specification is actually free. So you can actually download it yourself and look through Appendix 4, which is all about fire. Okay, so before we keep going, we're going to talk about the fire side for a little bit. So during a fire, so if you decide, please don't actually do this, but if you decided to, take your garbage can in your office and light a fire in it. Again, please don't do this. You would, the fire wouldn't get out of control right away, right? So it would stay in the garbage can for a little bit. Then, so if you had some papers, we're all in our offices, so it's just like paper everywhere. So if you, then some other papers might start lighting on fire. This is called pre-flashover. All right, this is when the sprinklers in your building can help you. This is when the sprinklers in the building can put out the fire. The basis of the field of structural fire engineering is, what if the sprinklers don't work? And in all of those fires that I showed you previously, the sprinklers were not working in the building. Okay, so the water actually was shut off on the day of 9/11 for the World Trade Center towers. For One Meridian Plaza, a bunch of stories were under construction, and that's where the fire broke out. So the fire did not get controlled until it actually spread to a floor that was not under construction, where the sprinklers went off. So so in the pre-flashover phase, this is where your sprinklers can help you. Once the entire room is engulfed in flames, once everything is combusted in your room or your compartment, that is called post-flashover. This is where the field of structural fire engineering lies. Okay, so we're talking about everything in your room has combusted, and the sprinklers are definitely not going to put that out. The sprinklers are not working, and the fire is able to spread uncontrollably. So at this time, you have about what's called a one-zone model. So it means that you really don't have a thermal gradient in your room from floor to ceiling. So everything is about one temperature. So you're not really considering a thermal gradient through the height of the space of your compartment or your room. So this is where the field of structural fire engineering lies. So if you start reading some papers on this, and they're talking about fully developed fire, post-flashover, this is what they're talking about. And here we can see sometimes, peak temperatures could be upwards of 1,000 degrees Celsius. So these fires can get really, really hot. Also, these fires include a decay phase, right? So this is something that's important for us to consider, particularly for steel structures, and there's a lot of research right now in this decay phase in timber structures. Eventually, your fuel is going to run out, or your fire is going to consume all of the oxygen in the room. At that point, you're going to start decaying in your temperatures. You're going to have this decay phase. This is important for steel, because that means that while during the heating phase, your steel members are expanding, during the cooling phase, they are contracting. Okay, so you're going to have different imposed forces and deformations on your structure during the decay phase than you would during the heating phase. This is important for timber because there are many instances shown of smoldering, right? So you might not visually see any fire, but behind the char layer, the timber might be smoldering, all right? So that means that you could just walk away from the structure, but heat is continuing to transfer through the section and char that timber section. And so when you come back a few hours later, you might not see a structure because it might have collapsed due to smoldering. right? So, so the decay phase is really, really critical. It's really important. All right, so let's go back to our flow chart. So we have the fire, we're heating our structural elements. At the same time, we're gonna have thermally induced deformations and forces, and we're gonna be degrading our material properties, right? I'm gonna talk about each of these for a second before I even dive into OpenSees coding. Okay, so degrading material properties, what does this mean? And for this presentation, I'm gonna focus on steel structures only. That's all I've modeled in OpenSees. Okay, so degrading material properties. These are the temperature-dependent stress strain curves plotted based on Euro Code 3. And so what are these degrading material properties? Well, we have a decrease in our yield stress and our ultimate stress. But you can also see that these curves are just not scalars of the 20 degrees Celsius curve here, the ambient temperature curve. They are changing as they go down. So we're seeing this more curvy linear behavior at the beginning of the curves in these small strain areas, right? So we're seeing this decrease in elastic modulus, but we're also seeing it's actually quite difficult to discern where the yield stress actually is as the temperature is increasing, because you would see down at the bottom at 800 degrees Celsius, there's very small linear portion of this stress strain curve. You have a very large curved portion of the curve. And so all of these properties are not actually degrading the same, right? So your yield stress is degrading one way, and your stiffness, your Young's modulus, is degrading another way, and then this proportional constant that's telling you how curved that portion is between the elastic and plastic region is degrading a totally different way, right? So so it's not just a matter of scaling your capacities of your members, right? So if you start thinking about column buckling or inelastic buckling of beams and columns, and even capacities of connections, you're going to see it gets complicated quite quickly. To add another wrench in there, this is all just for mild steel. So if we start looking at any type of steel that has been tempered, once you reach that tempering temperature, whatever has happened during the tempering stage is reversed. So if we start looking at bolts, we're going to see something totally different. So this, for connections, it becomes really complicated because your mild steel is degrading with capacity in one way, and your bolts are degrading with capacity in another way. And so you might be designing for some sort of ductile failure mode at ambient temperature, like plate bearing. But what you get at elevated temperature might be something totally different, because you'll see some of the controlling failure modes will swap. Another reason that this is really important is for those thermally induced deformations. So this is just a two-dimensional visualization of a beam with a concrete slab simulating 2D heat transfer through a steel concrete composite beam. So if we take this beam and we put a fire beneath it, what we see is the bottom of the beam will heat up, right? While the top of the slab will remain almost at ambient temperature. So the neutral axis is going to be shifting up throughout this fire. So even without zero load on this composite beam, we will see large deflections, right? So because all of the stiffness and the strength are degrading differently, and because it's nonlinear, and because it degrades in general, we do see an upward shifting of that neutral axis, and so we do see deformations just purely due to the thermal gradient that develops through cross sections. And so this is important to note for composite beams. It's also important to note for columns, and it really impacts particularly slender columns. Okay, so we have our fire, we're heating our structural elements. Now you all understand how our material properties are degrading. Let's talk about these thermally induced, we've talked a little bit about deformations. Let's focus on really forces here. So focusing on columns first. So if we had a pin column, thinking all the way back to beginning of your undergraduate career, we'd see column buckling shape looking like this. However, if we put a fire around this, okay? This steel column is going to want to expand. It can't expand because it's in a building, and the entire building around it is restraining that expansion. Because of that, these boundary conditions actually shift. So around 600 degrees Celsius, it depends on the column section, we see a shift of boundary conditions to, it acts almost exactly like a fixed column, because it can't expand and you have all of this thermal restraint on the top and the bottom of the column. And so what that does is, first off, it helps the column capacity. So that's, one thing is, it's a good thing. But the second thing is we're going to have these imposed moments in this column, in this gravity column, that we did not actually design this column for. So that can be, a really big issue as we're at the same time degrading the material properties of this steel. So we have these additional restraints due to thermal expansion. The same thing actually happens with our beams, and I'm focusing on our gravity members in particular because if we our lateral system actually has been designed for moments, and all of these additional axial forces that will be imposed in the members, and so we don't have to worry about them as much. But for our gravity beams, so if we look at just a snapshot of the end, we have our girder, we have in the US we call this a shear tab, I know elsewhere it's called a fin plate, and then we have our column, and typically just a ½ inch gap, so about 12 millimeters. I think this is my only inches in there. I think the rest of them I got I did switch over. So during a fire, this beam is going to want to expand. Plus, we have those very large deflections of our beam. So we're going to have a lot of rotation in this connection. Eventually, that gap's going to close. And once that gap closes, this connection cannot rotate anymore. So we've bound up this connection. We have an induced moment in the connection. And this beam is expanding and keeps expanding, right? So we have this axial force in the beam that it was not designed for, and we have a moment in the connection that it was not designed for. And so what ends up happening is we have failure modes that are not expected. So this is actually a picture from a test I did during my PhD, where, and this isn't the only time this happened, this happens over and over again, where you see fracture of this plate right outside the weld region, due to the axial force on the connection, and due to the imposed moment on the connection. We also see bolt shear fracture. This is why the World Trade Center 7 collapsed. It's bolt shear fracture, and we'll see local buckling of this bottom flange. So as this bottom flange is bearing on the column, we actually see local buckling of that bottom flange. Right. So we have all these imposed moments and deformations and forces that we just did not consider at ambient temperature, and they're all happening as our material properties are degrading. Okay, so just to kind of recap this, we have our fire and our structure. We're going to have excessive deformations of our beams and our girders. We're going to have thermally induced forces and moments. This actually leads to gravity column buckling and connection failure. You can see buckling of this column here in the simulation. And on top of it, in order to redistribute the loads, what we're going to have is catenary action of our slabs. Okay, so the redistribution of the loads is really dependent upon the strength of our slabs, right? And so if you start thinking about how you're going to simulate this, what is most important is that you need to be able to simulate the behavior of your gravity members, your gravity framing system. The behavior of your lateral system is important, but that's not really where we're going to see the damage in the building. Okay, so during an earthquake, we see damage mainly in our lateral force resisting system, but in a fire, we see it in our gravity members. We need to be able to simulate load redistribution through our catenary action of our slab. So we have to be able to simulate three-dimensional behavior. And then lastly, we have to simulate large plastic deformations that we're going to see due to those deflections. All right, so where does OpenSees come in here? Well, number 3, right? OpenSees is really good at simulating large plastic deformations, all right? So it seems like, hey, if we can incorporate temperature-dependent material properties, we should be able to actually simulate 1 and 2 and simulate the behavior of our steel structures in a fire. So that's where I'm going to go next, is how we actually implement this in OpenSees. So there is OpenSees for Fire at this website here. This is actually not what I'm going to be talking about today. OpenSees for Fire was first developed at the University of Edinburgh in 2009 and does everything that I'm telling you it can do, but is not really open sourced, and it does not work off the most recent version of OpenSees. Okay, so for all of you doing earthquake engineering, you go onto GitHub, you pull the latest and greatest version of OpenSees that Michael Scott has updated, and that's how you're working, right? That is not what OpenSees for Fire is. So that is not what I'm going to talk about today. What I'm going to talk about is how can you, in the same version of OpenSees that you're working in for earthquake engineering, how can you do everything that I'm talking about doing? Okay, so we are working in the latest version of OpenSees, and we're making sure that researchers can actually do structural fire engineering in an open sourced environment in the latest version of OpenSees. All right, so in order to do that, we developed 5 examples, and I'm going to show you a link for these examples. So you can actually download all the TICL files and you can run them as much as you want. And there's a lot of information on the webpage that we developed. So we thought, well, we have to go through and we have to actually benchmark our modeling methodology. We have to make sure that the latest and greatest version of OpenSees can actually simulate everything that I'm talking about. And so in order to do that, we went just step by step. So the first thing was, well, we have to simulate that thermal expansion, because that's going to be really important to simulate, because that is what is causing these thermally induced deformations and forces. So we did that through 2 examples. The first being just the simplest of examples, where we just heated up a beam and we just measured that thermal expansion. The second example is we heated up just half of the beam. All right, we added a node and support in the middle, and we measured the axial force in the other half of the beam. Right. Then we said, okay, well, now that we know how to simulate thermal expansion, we need to simulate our beam behavior. Okay, so let's take a simply supported beam, let's subject it to a fire, and let's look at the deflection. And let's look at how does that deflection change if we use a linear transformation or use a co-rotational nonlinear co-rotational or nonlinear transformation. How does that, how many fibers do we need along the length of the beam? How many steps do we need in our OpenSees analysis? And then once we were able to benchmark that, we moved to frames. So we looked at a one bay frame and a 2 bay frame, and putting a fire in each of them with mechanical loads and looking at the behavior of the beams in these frames. Okay, so I'm going to walk through and show you all the results from these. Okay, so here is the link to the webpage. There are, of all 5 examples, there is a lot more information than I'll show today in those examples. It walks you through absolutely everything, and it tells you why we chose to do certain things. It also it gives you access to all the TICL files. So in every single one, we used the Steel 01 thermal. This is the Eurocode 3 stress strain, temperature dependent stress strain curves, including strain hardening. When second order effects were not considered for the thermal expansion examples, we used a linear transformation. When second order effects are considered and are important, basically anytime you're putting a structural load on something for fire, caveat, we used the co-rotational transformation. We used displacement beam column elements, although now you can use force-based elements if you would like, but at the time that we made these, those were not available in thermal elements. And in the number of steps, you'll see we do have kind of a lot of steps for how simplistic these models are. We found that you really do need a lot of steps in order to get the correct answer. And I'll show you how we actually determined what the correct answer is. Okay, so how do you do thermal loading? So, the mechanical, I'm assuming all of you know really how to do mechanical loading in OpenSees, but the thermal loading can be a little bit tricky. Basically, OpenSees allows you to do 2 or 9 points through the section, like nothing in between. So hopefully in the future we can get something in between. It just seems like a little or a lot. And so you have to define where those 2 points are. And then OpenSees linearly interpolates between the two. As you saw all the way at the beginning of this presentation, there can be quite a big thermal gradient through the cross section. And so if you actually do have a thermal gradient through your cross section, you're going to want to use those 9 points because that linear interpolation is not going to be accurate at all. So for those sections that we just had, there was no thermal gradient. We just used 2 data points, and then when we did have a thermal gradient, we used 9 data points. We chose to do it in this way that I'm showing on the screen, but you get to choose where those data points go. So you can define exactly where those points are. OpenSees does not do heat transfer analysis. So all of our heat transfer analysis was performed in Abacus. You can also perform it in LS-DYNA. You can use, there's a free software called Ozone that you can do it by hand if you really want to. It's not super complicated, but we used Abacus and then pulled the nodal temperatures out of our heat transfer analysis and used that as inputs into our thermal analysis. So you can also have 2 different types of loading. So for something that has like 2 data points, you might have linear loading where you're just saying this entire section is at 1200 degrees Celsius in 2 hours, and it'll just linearly thermally load the section. If you actually have a design basis fire, so you're actually doing 2-dimensional heat transfer analysis, I'm showing here, then you're going to want to use the temperature history from the fire itself. And you're doing that just through text files. You're just importing text files and referencing them in OpenSees. Okay, so let me show you some examples, the results of these examples, and then I'm going to show you very, very briefly how we actually applied all of this modeling methodology. And then I'll, give you all a call to action, and you can solve the rest of the problems with OpenSees and Fire. So for our thermal expansion, for just example 1, we're just purely comparing it to the Eurocode material model. So the measured thermal expansion can be measured, can be divided by the original length and just compared straight to the temperature dependent thermal expansion properties of steel. And you can see that it compared really well. So OpenSees was able to simulate pure thermal expansion. The second example that we did is we started changing the temperature of the right side of this beam to 1180 degrees Celsius from 20 degrees Celsius. And throughout that time, we were measuring the axial force in the left side of the beam. And we simulated the same thing in Abacus and then compared the 2 results. You can see that they are very, very similar. And so said, okay, well, OpenSees is able to simulate the thermally induced deformations and forces within a beam without any mechanical loading. So we next said, okay, well, let's put some mechanical load on it and start looking at the impact of restraining node 2 to thermal expansion and also to using a linear or co-rotational transformation. AB here, so the red lines are Abacus. So you can see that we have really good correlation. So the OpenSees was able to actually simulate the vertical displacement at the midspan of this beam using both linear and nonlinear and restrained and unrestrained connections. And it compared really well with what we were getting out of Abacus. Okay, so lastly, we were looking at these frames. In example 4, we compared the results to Abacus. In example 5, we compared it to testing data. So this is an actual experiment that occurred. So in example 4, we had a 1-bay frame. It's fixed on the bottom, and at the top, it was restrained against movement in the plane. Then beam was loaded with a distributed load. And we subjected the entire structure to the ISO 834 fire curve, which is pretty much the same as the ASTM E119 fire. So this is the standard fire. And we just looked at the midspan displacement of this top beam. Displacement and particularly beam displacement is usually used as kind of like an indicator for structural performance in fire. So this is why this keeps coming up. So you can see it compares really well with what we got out of Abacus. And so OpenSees, we said, can actually simulate the frame behavior really well. We then did a similar simulation in a 2-bay frame with a fire just in 1 bay. We looked at the horizontal displacement of this U1 node here and compared it to our testing data. And compared really well. So we actually had a horizontal load on this, and we had vertical load on this, and then we subjected it to the fire. Right. So OpenSees was able to do these validation studies really well, but some of the limitations is that you'll notice everything was in 2D, so we did not simulate catenary reaction of the slab. We didn't actually simulate a slab at all, so it was just pure steel structure. And all of the connections were pretty much restrained. So we weren't really looking at like a pin roller situation and allowing for that restraint, except for in the thermal expansion model. Okay. So a question that we had is, well, in a lot of these post-earthquake fire scenarios, and in this post-earthquake fire research, everyone's simulating these lateral force resisting systems. Like, no one's simulating the gravity system in these post-earthquake fire scenarios. And so let's kind of, like close the door on this topic, and show that you're really not going to see much in a post-earthquake fire scenario. So in order to do that, we actually performed a sequentially coupled incremental dynamic analysis and incremental fire analysis on a 2-dimensional moment resisting frame, applying all of the modeling methodologies that you just saw. We performed this, we put the fire in the compartment on the lower left-hand corner, because we actually performed a post-earthquake fire analysis using multiple different fire scenarios and multiple different compartments, and found that this was the worst behaving compartment in the building. Right? So I'm kind of like skipping over an analysis study here. So we considered 3 different ground motions, and then we with varying the PGAs. So just scaling the ground motion from 1, 3, and 5. And then we consider 3 different maximum temperatures of 10 different fires. So in each set, there's 10 fires. So we were varying the opening factor, we were varying the material properties in the compartment, and we were varying the fuel load in the compartment to get these fires. Right. So we just wanted to kind of bound the situation. So this is why we chose these scalar ground motions. We could have kept going and increasing. And I realized, normally incremental dynamic analysis, you just keep increasing the ground motions until collapse. But if it collapses in the earthquake, it's no fun to analyze in the fire. So we did not want it to collapse in the earthquake. We just wanted to see damage in the earthquake and then look at the impact of multiple fires after the earthquake. We also just solely subjected our building or our frame to all of these fires. So we are comparing the fire only behavior to the post-earthquake fire behavior. So it doesn't matter that there was an earthquake before, or, you know, and in what scenarios are you going to see a lot of damage in a post-earthquake fire scenario to your lateral force system. Okay, so just some, you know, brief results. This is all for the non-scaled PGA ground motion, right? So our three target maximum temperatures were 600, 800, and 1,000 degrees Celsius. And what we found is that, and what I'm showing here are interstory drifts of the frame. The red lines are the average interstory drifts for only the fires, and the black is the average for FFE, fire following earthquake. And what we found is that the largest difference between the FFE and the fire only occurred for the 600 degrees Celsius fires, right? Which is sort of to be expected. We actually saw a lot of collapse in the 1,000 degrees Celsius. So I don't know, you know, looking back at the material properties, like I only went up to 800. At 1,000 degrees Celsius, our steel has basically no capacity. So, you know, that we really wouldn't expect a lot of dispersion in the behavior in that 1,000 degrees Celsius fire. Just everything kind of heated up really quickly and collapsed. But at these lower temperatures, when steel actually has some residual capacity, we did see some differences between the FFE and the fire only analysis, although very different, you know, still very close. You know, the red line and the black lines are still very close to one another. If we looked at beam midspan displacements, though, you know, we saw higher temperatures led to larger midspan displacements, which is to be expected. The duration of the fire played a very large, important role in this. We saw larger midspan displacements when we saw longer duration, longer heating phases. And then for the 800 degrees Celsius fires, that had a shorter heating phase, less than 30 minutes. Where is that? Oh, maximum gas temperature. Okay, we saw a lot of dispersion in the data. So, you know, what the purpose of showing you these plots is what you can do when you actually can simulate the behavior of steel structures and fires. Is you can start actually taking a lot of the, you know, really great modeling methodologies that have been applied to earthquake engineering, and you can apply it to fire. So performing these coupled, you know, IDA, IFA analyses in order to really kind of bound the entire problem, or even just performing like straight IFA analysis, so that you can actually bound the problem. And with OpenSees, you know, these models run really, really fast compared to, you know, I used Abacus for my PhD, so. You can actually do a lot. You can run a lot of models with these in a very short period of time. Okay, so let's look to the future. What are some challenges? You know, everything I just showed was with the lateral force resisting system, because we still need to figure out the connection problem. You know, if we're going to simulate what I'm showing on the left, this is not an idealized pin. This is not going to be able to rotate indefinitely during a fire. And we have to be able to simulate that binding up of the connection. And something that we're working on right now is being able to simulate each bolt line with a temperature-dependent constitutive model, considering bolt shear fracture, bolt bearing on the beam web, and bolt bearing on the shear tab. So the 3 springs in series simulate these failure modes specific to the connection geometry. There's also a gap element spring that can simulate the closing of that gap. So once the gap closes, the connection cannot rotate anymore. Okay, so being able to actually consider that in the connection. We've been able to somewhat implement this in OpenSees, but hopefully this summer we'll be continuing on our journey and finishing that up. And you know, again, this allows us to actually simulate the rotational stiffness of the connection as a function of temperature. So, and consider the individual failure modes of our connections with temperature dependent material properties. We are also working with the National Institute of Standards and Technology in the United States and the National Fire Research Lab at NIST to benchmark all of our modeling methodologies against some of their experiments. So as soon as we can get this connection model benchmarked, we're going to be or up and running and working. We're going to be benchmarking it against a number of composite beam experiments that they performed at their lab. These are 12.8 meter long steel concrete composite beams. And they were all subjected to the standard fire or something close to the standard fire. And we have all of their data and we're ready to kind of benchmark our modeling methodologies to show that OpenSees can be, a really great tool for simulating composite beams with connections in fire. Once we're able to benchmark that in 2 dimensions, we can move into the 3-dimensional realm, where NIST is actually performing a number of 2-story compartment fire tests in their laboratory, and we are working with them to be able to benchmark our models against that data. So I think I've gone a bit over time, but most of the work that I just showed you was developed by Walker Matalozzo, who's just graduated with his master's degree. He is going to be an engineer at Katina Engineers in Portland. James Gordon is the other graduate research assistant working on the project. Michael Scott has been a big help in teaching me OpenSees and allowing us to kind of tell him when new updates of OpenSees has created bugs for fire analysis. Kevin Mackey at University of Central Florida is helping us as well. And Lisa Cho at NIST is providing access to all of their data. And this research is funded by the Pacific Earthquake Engineering Research Center and the American Institute of Steel Construction. So thank you so much for letting me share all of this with you, and I'm happy to take any questions.
Thank you for the presentation, and yeah, any questions from anyone in the audience? Usually it takes time to warm up and come on, get the questions. So yeah, thank you for the presentation. I'm pretty sure like someone who wants to work on the fire, this will be like a amazing starting point for them to understand. Good. I had no idea like before this like how to do, and because that's not our research, but like still having an idea is important. But yeah. Any questions from anyone? No. We got one.
Well, thank you for the very nice presentation. I have a question about the gravity beam connection you just shown toward the end of the presentation. Can you go back to that slide? I think this is, of course, a very nice topic that associated with the realistic connection in the gravity beam. Here you have this rigid element in the right figure. Would you please tell me where do you define this rigid line from the left figure? It appears to me you have to assume something plane remain plane or something like that. Would you please?
Sorry, I muted myself. That is a really great question. Thank you for asking that. So these are actually 0 length springs. So this is, I'm showing, some length to them so that I can point to some springs, but there's 0 length spring elements, and they would be defined. You can define them at the bolt line, is where I would recommend defining them. And consider the full rotation of, basically you are considering plane sections remain plane for a rotation of the beam in this area. Does that answer your question, or?
Yeah, that's my question. Thank you.
Okay, yeah, yeah.
So you're
And
not,
I would say,
sorry.
oh, sorry, go ahead.
So you're not modeling the gap between the vertical member and the horizontal member then? Because you're assuming a zero length member, right? So the initial condition.
You are modeling, yeah, you are modeling the gap just through this gap element spring. So you're modeling the gap through a spring.
So the gap element, to my knowledge, is like, so this is the physical gap, right? So
Yes, that is the physical gap. So basically, as if the connection like rotates a certain amount, then you say, okay, the gap has closed.
yes. So okay, that's what the element is. Okay. Cool.
Yeah. And this, I mean, I will say, so, you know, this is really helpful to be able to simulate the full building behavior. So if you're, you know, interested in simulating just like the isolated connection, I would not recommend, you know, just using these constitutive models. You can just model everything explicitly. But if you're modeling the full building, modeling every single bolt is going to be quite computationally expensive, and your model's going to take a really long time to run. Something in the chat. Okay.
There is a question in the chat.
Okay. Yes, about hybrid simulation. Yeah, I am not working on hybrid simulation, but there are a number of researchers that are working on hybrid simulation. I know ETH has made a lot of headway with hybrid simulation and fire. Nigar Khorsani at University of Buffalo is working on hybrid simulation and fire, as well as Khalid Masalam at UC Berkeley. So there are a lot smarter people than I am, and they are all, you know, definitely ahead of the game with hybrid simulation and fire. And I think it's really exciting. Fire tests are incredibly expensive, so being able to simulate the, you know, individual, to test an individual member and then simulate how it impacts the whole building would be very exciting. I know there are others. I probably left out a few others working on hybrid simulation and fires. So,
Any other questions?
I don't know if they're using OpenSees. I think ETH might be using Sapphire, but yeah, I don't know if they're actually using OpenSees for that hybrid
Dr.
simulation.
Dimitros, I think he presented here, so he was using steel structures and OpenSees, and there is a whole bunch of team there, I think. And I think like on fire, like the other universities in China, Dr. Shenzhen Lu, because he presented something on the fire and like simulations and stuff in one of these meetings, and that was pretty cool too. So maybe they are using it as well.
Yeah. I know Sapphire is being used for some of it, and I know in the chat they're agreeing. Yeah.
Okay. Any other questions from anyone else? This may be like a new topic to most of people, and
hopefully this is a launching point for people, and we can get some more really smart earthquake engineers involved in this, because I do think there's a lot of parallels with especially understanding just, you know, plasticity is so important for fire. So you know, all of you earthquake engineers out there have a really good handle on that, and so, you know, test out all of our examples and then, you know, solve some of our problems.
Yeah. I mean, if there are no more questions, then we can, I mean, I guess like you can ask her, like send an email. I hope that's fine if they have questions.
Yeah.
Yeah.
Yes.
So thank you for the present. Oh, one more question. Okay.
Oh, easiest tool for simulating heat transfer. So I know Ozone is a free software that does heat transfer analysis. I use Abacus, but I've always used Abacus. LS-DYNA is it can also do heat transfer analysis. For steel and concrete, it's pretty straightforward. I don't mean to like diminish some of my own work, but heat transfer isn't too difficult between steel and concrete. When you get to timber, it becomes a little bit more complicated because you have char and you have pyrolysis, and you need to actually simulate the chemical changes. But for steel, it's pretty well benchmarked if you just use the Eurocode properties. Hopefully I answered that question.
Any other questions? Because these questions peep in like last minute like this, so that's why I keep asking.
It's all right.
Okay, if there are no more questions, then we will finish it today. Like, thank you for the presentation. It's really interesting, and I'm sure it will be a nice starting point for everyone. And thank you for answering the questions. We really appreciate your time. Thank you.
Thank you for inviting me. This was fun. And anyone, please feel free to shoot me an email if you have questions on any of this.
Cool.